Okay, hi everybody. So today we're going to start 5.1, which is all about areas and distances. And so in this section, what we're really going to do is we're going to go ahead and take a look at a function, any function, and then we're going to try to find the area under the curve. So that's our goal for this section, is to kind of look at a function and look at some bounds and see if we can find the area under that curve. And I'll show you what that means in just a second. But before we get started, I need to go over some notation, which is called sigma notation. And so the reason that we need to do that is because using sigma notation is going to help us evaluate the area under the curve. And I'll show you what I mean just right now. So what is sigma notation? So sigma notation is a notation that looks like this. It's a big old funny looking E. That's all it is. It's nothing crazy. And it looks crazier than it is, but why do we need to use sigma notation? And so what sigma notation means that we're going to sum everything up. So just a big old E meaning sum. That's all it means. So for example, if I wanted to take a look at the sum of the integers 1 through 20, so I wanted to add 1 plus 2 plus 3 plus 4 plus all the way to 20, right? Well, I don't really want to write all of that out. So what I would do instead is I would say, okay, instead of writing 1 through 20 all the way through, going plus 4 plus 5 plus 6 plus 7, and you get it, right? So instead what we'll do is we'll say that this is actually equal to the sum, and sum, this is going to be our big sigma. So this over here means sigma, capital sigma, of I from I equals 1 to 20 for each I. So what's going on here? So the reason I is equal to 1 here is because we're starting off at 1 here. So this will always match with your starting point, or whatever it is that you're using to start your summation at. And then the 20 is just wherever you're ending. And this just means that from here, we're going to input into here and add each next one over and over and over again. And so this part here is what we call the index of our sigma. Now, our index doesn't always have to start at 1. It could start at 0. It could start at 3. It could start at 5. It doesn't really matter where it starts, as long as you know where you're starting and when you're plugging in the values. So let's just do one more quick example. And let's say we wanted to sum all the even numbers all the way to 100. So right now, we're not actually evaluating these right now. We will eventually during this video. But for now, all we're doing is we're just summing them up. So 2 plus 4 plus 6 plus 8 plus ... Let's say we're going all the way to 100. So if we're going all the way to 100, right, we want to figure out a way to write this as a sigma notation. So in order to do the sigma notation, I know that I'm eventually going to have to write that big sigma. And then from there, I need to figure out where I'm going to start, what's going to go here, and what's going to be my ending value. Now here we're going in through all our even numbers. So we're going to go from 2 to 4 to 6 to 8. So we need to figure out how to start from there. So what we're going to do is another way to write an even number. Let's think about another way to write an even number. We can write as, let's say, 2 times n for now. It's not going to be n for this, but if you multiply any number times 2, that's going to give you an even number. So what we're going to do for our sigma notation is we're going to keep a 2 here. And since our first term is a 2, we want to make sure that our I value here is 1, so that when we plug in 1, we get 2. And then when I equals 2, we get 4. And when I goes to 3, When we plug it in here, we get 6, and so on and so forth. And so this is actually going to stop at n I equals 50. So I equals 50, we will stop, and that does not look like a 50. At I equals 50, we will stop, and then our last one will always be, if I equals 50, here, plug in 50 into here, we'll definitely get 100. So we get our ending value. So that's what sigma notation is. It's just a different way to write, a different way to write adding things over and over and over and over again that carry on that same pattern. So at the first example, we were just incrementing by 1. So that's what we just had an I there. There was nothing happening. There was nothing changing. Here we were adding all the even numbers. So we need to adjust that middle term accordingly. So let's generalize this. So in general, for our sigma notation, if we have our capital sigma, we will have our n value up here. We will have I equals 1. Again, it doesn't have to start at 1. It could start at anything. Or we could just put I, just for the sake of generalization, of AI is equal to A1 plus A2. Actually, I'm going to keep the 1. Plus A3 plus ... all the way to AN. So again, basically this is our index. This n here is what we call our upper limit of summation. So it's, as far as we're going to go, we're going to increase I all the way to this number n. That's all that is. So this is our upper limit of summation. And we're going to really use sigma notation to approximate values under the curve for the beginning of this, and then we'll just do it using antiderivatives later on. But basically all you're doing is, this is your I, you plug that in here, and that's why at first your I is equal to 1. Here's your 1, your second index, your third, all the way to your nth index, and then you will just sum them all up. Okay, we'll do a couple examples and it should get easier. You will see this again in Calc 2 for sure when you're doing series. So don't let this scare you. It's really not that bad. And you'll see it again in Calc 2. You might not do it exactly the same way as we're doing it now, but it's a good way to kind of just get a feel for the notation and some of the properties you will use again in Calc 2. So please pay attention. Okay, so let's do a few examples. So let's do, so this is something you want to box so that you get used to it. This is just your general sigma notation. And now we'll move into a couple of examples. And we'll do a lot for this section just because it's something fairly new and I want you guys to get used to it. So for the first example, I want you to write the sigma notation for 3 to the I. For, let's say I is going to go from 1, 2, 3, 4, and 5. So right here, I'm telling you what's going to be that AI inside the sigma notation. So this is what's going to match with this part here. That's what I'm giving you. And I want you to do it for I equaling 1, 2, 3, 4, and 5. That's what I want you to do. So just get some practice with writing the sigma notation. So I know, because I have sigma notation, that I'm going to need my capital E, my capital sigma, and I need an index. And then I went ahead and already gave you that big term, or the thing we're going to be summing. So this is going to be 3I is going to go in here, 3 to the I. And now let's take a look at what, I swear this was a 5. Now let's take a look at where we're going on for our I values. So we're starting off at 1. So that's going to tell me that this bottom index is going to start off at 1. Again, they don't always start off at 1. They can start off at random numbers, so don't let that fool you or anything. And then the last thing that I'm going to do is I'm going to end up at 5. So that's what's going to be my upper limit of summation. So just to get you guys to practice, if we write it in the form, in the general form, we would get 3, 1, 3 to the first power, plus, so right here, all I'm doing is iterating through those indexes. So I have I equals 1, I plug it in here, 1. Now I'm going to do the second one, plus 3 squared, because every time I iterate through a new one, I need to add the previous one. And now I'm going to do 3 cubed, because that's the third one, plus 3 to the fourth, plus 3 to the fifth, and then there I stop. That's my last one. So basically, that's how summation notation works. And again, we'll do a few examples before we get and dive deep into areas under the curve, because getting a great understanding of sigma notation is really going to help you easily evaluate those areas under the curves when we're doing upper and lower limits. So just stay tuned for that. So let's do another example. Move on to the next page. Okay, so for part B, we are going to do an example where we are given the sum and we want to write the sum in sigma notation. So the sum is going to be 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25. And our job is to look at the sum here and then to recognize what the summation or the sigma notation would look like. So that's what we're looking for. We're looking for when that happens. Okay, so in order to do this, what I want you to notice is go ahead and look at the first term. The first term is 1. It doesn't really tell you much, but then I notice that all my tops are staying the same, and so they're all going to be 1. So when I start off my sigma notation, I'm going to write my big E, and since I notice that the numerators are not changing, that tells me that my numerator for my argument is just 1. Now what is changing is the denominator. And so if I look here, this is 4, this is 9, this is 16, and this is 25. And what I do notice about them is that they're all perfect squares. And this is 2 squared, this is 3 squared, 4 squared, and 5 squared. And this is technically over 1 squared. So that tells me that in here I have I all squared. And since I'm starting at 1 for my 1 squared, I can write I starts at 1 and it ends at my last perfect square, which is 5 squared. So we'll write 5 for our n value. Okay, and then you could always check that by iterating through and going, okay, if I plug in 1 into this, I get 1, and then I plug in 2, I get 1 over 2 squared. Okay, so now let's do another example where I'm going to give you the sum and it's your job to plug in the values and check what it looks like and evaluate them. So for example C, we are going to evaluate let me zoom in a little bit. We're going to do the sum, actually, the sum of 5 for k equals 1. Oh, wow, that k. For k equals 1 of k times k plus 1 over 2. Okay, so for this, what we want to do is we want to evaluate this sum. And to evaluate this sum, all we have to do is, I decided that I wanted to change my argument this time. Instead of having i's, I have k's. So when you're evaluating sums, what you want to take a look at is, does this match this because it should, because this is what you're going to be plugging into your summation. So you want to make sure that that matches, and it does, because if I have I, then I don't have anything to plug it into, and that would be a different scenario. So make sure that it matches, and that's why I wanted to show you what it's like to plug in different values for, it doesn't always have to be I. A lot of times you will see that this is like J or I or K or N. So just be aware of that. Okay, so now to evaluate this summation, what we want to do is we're going to plug in our values for K into here and sum the next ones over and over and over again. So now what we're going to do is we're going to, once we plug that in, we're going to do, if I plug in 1 into my first K, I'm going to get 1 times 1 plus 1 over 2 plus 2, if I plug in the next value for K, times 2 plus 1 over 2 plus 3 times 3 plus 1 over 2. And then the next one is 4. 4 plus 1 over 2. And I think you guys get it. The last one is 5. 5 plus 1 over, probably should have stopped at 4 because I think you guys get it. Okay, now after that, all we have to do is evaluate. And so I noticed that they all are getting divided by 2. So I can go ahead and actually factor that out of all of them, which will bring us to our next, after a few more examples, we're going to talk about the properties of summations, and hopefully you can see where this is going, but I can factor out that 2 out of all of them. And so I can say 1/2, and then I'll factor that out. And then when I factor that out, here I'm going to get 2. So I'll get 2. And then here I'll get 2 times 3, which is 6, so plus 6, plus 3 times 3 plus 1, which is 12. So I'll get 12 here. And then plus 4 times that 5, that's going to be 20. And then 5 times that 6, which is going to be 30. So all I did was I factored the 1/2 out of all of them since they all had that in common. And then I multiplied these two together to get my top. And now if we evaluate this, we'll get 1/2, and then we'll add all the insides together, and we'll get 2 plus 6 plus 12 plus 30 plus 20 plus 30, and that should equal 70. And so now if we multiply 1/2 by 70, we get 35. And so we finally finished evaluating that function. And I was going to keep going, but I think that I'll just have you, no, actually, we'll do this next one. So just because I think this is a good one, especially when you're moving forward to Calc 2, just to remind you about these cool factorials or exclamation marks. Okay. So here, same thing, I want you to try this. So here, this one's a little bit different. Our K is starting at 3 and not at 1 or 0 like we're used to. So what we're going to do is we're just going to go from here. So this one won't be too long because we're starting at 3 and it ends at 4. So if I'm starting at 3, I'm going to plug in 3 into K, and I'm going to get 3 factorial times 2. Plus, I already did 3, now I get to do 4, plus 4 factorial over 2. And then if we evaluate this, we'll get 3 times 1 times, 3 times 2 times 1. Remember that a factorial just means that you'll do 3 times 2 times 1, decreasing, over 2, plus 4 times 2, 4 times 3 times 2 times 1, all over. We can simplify this. This 2's in common, 2's in common here, and we'll get, we'll get over here on this side, we'll get 3 and then we're adding the 12th. And so then here we end up with 15. So that's what we get if we evaluate this fraction, this summation here. So it's a lot of plugging in, and it just takes you getting used to. Not too bad. And then actually want to do one more example. I know there's a lot of examples here, but I think it's good. Good practice on the summations so that we get used to them. And then we get the sum of, this will be our last example, and then we'll head into the properties of summations. And this time I'm gonna make my index n just to switch it up. And we'll just leave it as 3. So here's the thing. For this problem, we have an index. Our index is n, and it's 2. But my argument inside is just 3. Actually, n's not even involved at all. So we don't have anything to plug it into. So what we're gonna do here is, since n is the thing that changes each time we plug something in over and over and over again. In this case, we don't have that. So it's not going to change, but we still have to iterate through. So we'll do 2. When we start at n equals 2, and we need to go to n equals 5. So right now we're at 2, and when we plug in 2, nothing changes. We're still gonna get 3. Now we're gonna plug in n equals 3, but there's nowhere to plug it in, so we're just gonna get another 3. And now we're gonna do our n equals 4, nothing to plug it into. And now we're gonna do n equals 5. And so now when we evaluate this, we just get 12. So notice something here. We get 3 times 1, 2, 3, 4 gives us 12. And we had to iterate through 4 times. So if there's nothing involved there, then it's gonna be that many times of what that number is, of how many iterations you went to for that constant, which is actually gonna lead us nicely to our properties of summations. So let's go ahead and go over the properties of summations. Okay, and then before we go through the properties, I know if you're doing the homework, they don't actually ask you questions directly about these types of problems. I'm not 100% sure why they don't, but when we're gonna go over Riemann sums in this section, this is why the section is gonna be a little bit longer than what it's meant to be in your textbook, because they go over Riemann sums and evaluating sums. You can't really do that without recalling all these properties. You might have learned these properties like in your geometry class in high school, I think is the last spot that you actually learn them in. But I think it's a good thing that we're going over them, because, I mean, how else are you going to know? The text doesn't actually underline these formulas for you. They'll have you recall them from some time, but they don't go over them directly. So we're going to go ahead and go over them just to make your homework a lot easier in the long run. Okay, so let's do these properties. So the first property actually has to do a lot with how we handle example E. So for the first property, let's do block, we will get that if we have the sum from I equals 1 to n of k times our argument ai, then actually it has a lot more to do with this 1c here, how we factored this out. But if we have something like this, then because this k doesn't involve any I, we can factor out that k out of the summation because it has nothing to do with the index of our problem. And so instead we can evaluate k times n I equals 1 of ai, which is really nice because I didn't do this earlier, but if we take a look at example C, we could have, at the very beginning, we have a 1/2 out in the front, is just brought that 1/2 out. but I didn't do that because I wanted you to see the property. So now you know you can factor out any constant out of a summation, just like when you're taking the derivative, you can factor that out. A lot of the same properties as derivatives, actually. And now that takes us to our second property, which is if we have the sum of from I equals 1 to n of some ai plus or minus some bi. This is going to equal the sum from I equals 1 to n of ai plus or minus the sum of I equals 1 of n of bi. Kind of like derivatives all over again, just like you can take the derivative of all of this, you can also take the derivative and break it up like that. That's all that means. And now property 3 actually is the one that has to do with example E. So if you have the sum of from I equals 1 to n of some constant k, similar to what we had here, here I'm starting it at 1 so that you can clearly see the property. This will equal n times k, which makes sense because if we look back at this example, we iterated through it 4 times and our answer was 12. So basically up here, we ended up with 3 times 4. However many times we iterated through it, and our constant was 3. So now for example 4, what we're going to want to do is our next property, which these are 4 through 6, I'm going to warn you right now, are the most important ones for Riemann sums. These just make 1 through 3 really just make your life a lot easier. But 4 through 6 are new, and they're formulas that you need to memorize when you're doing Riemann sums. And we'll do a few examples of those as well. So we're going to have the sum of I. So let's just say we have the sum of I. So this means that we are adding all of the integers over and over again, just like we did in the first question. So here we have the sum as I goes from 1 to 20 of just I. So that means that you were adding consecutive numbers over and over and over and over again until you hit the last upper sum, okay, or upper limit. And now instead of having to add them over and over and over again and say, okay, I have to add 1 plus 2 plus 3 plus 4 plus 5 all the way to 20, instead we now have a formula for it, which is that if you are adding consecutive numbers over and over again, then it's going to be equal to n times n plus 1 all over 2. And there's actually a really nice story to this as well. So there's a mathematician named Gauss that, I don't know, there's like mixed stories about this, but that his teacher was giving him the class busy work, and they said, hey, he told his students, hey, you need to add all the numbers from 1 to 100 all together. So he needed to add 1 plus 2 plus 3 plus 4 plus 5 all the way to 100. And this guy, this smart little man, did it in like half a second or like a minute or two, because he realized that there was a pattern. And so that every time you wanted to do 100, you can just plug it into here and it'll give you the answer. So for example, let's actually do an example right under this. It'll be a short example. That for example, if you wanted to add all the integers from I equals 1 to, let's say, 50, right? You don't want to go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way to 50. That's going to take you way too long. Instead, you can do the sum from I equals 1 of I, and then using that formula, right? Here, my ending value, my upper sum is n, which is 50. We would do 50 plus 51, or let's actually keep it consistent here, 50 plus 1 all over 2, which is the same thing as 50 times 51 all over 2, which is equal to 1,275. So now you know, if somebody asks you to write the sum of the integers from 1 to 1,000, all you have to do is go, okay, 1,000 plus 1,001 divided by 2. And I get my answer. I get my sum. Easy peasy. Not too bad, right? Pretty cool, I think. But I'm a nerd, so. Okay, next property, very similar to this one. But instead, we're going to do the sum from I equals 1 to n of I squared. And this actually turns out to be n times n plus 1, similar to that first problem up there, times 2n plus 1 all over 2. Yes, you do need to memorize it. Actually, I should put a star next to these because these are really important formulas, and we're going to be using them for our summations and approximating areas. So really important to know these. They'll make your life so much easier because nobody has time to be adding integers over and over again. Okay, so let's do an example of this. You know what? Why not? So let's do an example. We have, let's do the sum from I equals 1 of I squared to 20. So if we wanted to do this sum right here, we would do 20. And then I'm going to plug it into this part here, which is 21. And then we're going to do 2 times 20, which is 40, plus that 1, 41. All over, oops, and this should not be 2, this should be 6, sorry. I was looking up here and not thinking. But that should actually be 6. Notice that when I was about to write down the formula. It's okay. And so then we divide by that, and then we get 2,870. So that's if we do it for 6. And now our last one, if you can guess, this was I, this is I squared, and we're gonna do our last one's gonna be I cubed. So we get the sum from n of I equals 1 of I cubed is equal to n squared times n plus 1 all squared all over 4. Okay, and I won't do an example of that because I think you guys get it for these. Okay. So now that we learned all these properties, I want to do an example. So let's do a few examples just so that you guys get the hang of it, so that when we move into Riemann sums, it's super easy sailing from there. So let's do an example. Let's evaluate the sum from I equals 1 to 10 of 2i minus 1 all squared. Okay. So let's see. So for this, it might be a good idea that when you're learning these, right, so when you're practicing, is to kind of go back and maybe if you're doing your homework, write down these formulas all over again, because we're going to use these in order to manipulate our summation so that we can evaluate sums really easily. Because I don't really want to, I mean, we could, but this would take way too long, is go I equals 1, plug it in, add the next one, and type it in our calculator. But it's going to take too long, and I don't want to do that, and I doubt you want to do that either. So what we're going to do is we're going to use our properties of summations to be able to break this sum up and use our formulas here in order to find and evaluate that answer. So we're trying to add from 1 to 10 to 2i minus 1 all squared. And you want to use those formulas because, okay, yeah, this time I gave you 10, but what if I gave you 10 million or whatever, right? You don't want to do that for that many. So instead, we're going to do it for this, using our formulas to make our life easier. So the first thing that we want to do is, I would probably, since this one isn't too bad, this 2 out here doesn't really help me that much. So I'm going to go ahead and FOIL it out, or just use my distributive property here and go, okay, I'm going to go from I equals 1. And if I FOIL this out, I'm going to get 4i squared minus 4i plus 1. Okay. And then after that, what we're going to do is, we learned here that we can break them up. So we're going to go ahead and do that. And again, here, I'm being a little bit extra with the breaking up so that you guys can see it happening. So I'm going to break it up, and I'm going to factor out any constants that I don't need. So for this first term here, I can factor out this 4 out in the front and leave it as I squared. And then it's going to be minus the sum from I equals 1 to 10 of I. And again, here I have a constant, so I'll have that 4 in the front. And then my last one is going to be plus the sum from I equals 1 to 10 of 1. And now, if we take a look at this, here I have an I squared term, and here I have an I term, and here I have a constant term. So if we kind of go back and look at our properties, we already know how to evaluate something that's I squared given an n value. We know how to evaluate something with I given a value. And then if we have a constant, we learn that if it's just a constant, it's going to be n times k. Okay? So now let's go ahead and do that. Let's plug in the formulas that we know. So here we're going to get 4 times, and I'm going to do big parentheses over this. And remember that for this one, it was n. Let me just do this. It was n times n plus 1 times 2n plus 1 all over 6. So then if we plug that into our formula, we would get 10 for n, and then 11, and then 10 times 2, which is 20, plus 1, that's our 21, all over 6. And then we're going to do minus 4 times, now remember that for this one over here, it was n times n plus 1 all over 2. Easy. And so now we're going to plug that in. So we're going to get 10 times 11 all over 2. And then for our last one, it's just a constant. So it's just going to be plus 10 times 1. So remember that for this one, we're just going to use n times k. Okay, so I'm just being extra, breaking it up for you so you see where all this is going, because it's all really new. Takes some time to learn. And now we just evaluate and simplify, and I did this ahead of time so I wouldn't waste time, but then we'll get 1540 minus 220 plus 10. We simplify that, we'll get 1330. So not too bad, not too bad. And now let's do one more example just so we make sure we actually get it down real good before we go into doing these sums for infinite numbers. Remember, calculus is called infinitesimal calculus, so we gotta try to do things for infinity because that's how we get things very accurate. Okay, let's do one more example. Okay. So we will evaluate for n equals 25. Now we're going to use the sum from n equals, I equals 1 to n. for 3i minus 3 all over n cubed. Okay. So remember, good idea to write your formulas out so you know what you can use and what you can't use. So before we get started, our index here, what we're iterating through, is I. So actually, let's change this to n squared. So what we're iterating through is I, not n. So be careful here, because n doesn't seem like something that you can actually factor out, but you can, because let's think about this. N has nothing to do with the index. We're not iterating through n. N is a set value right now. N equals 25, actually. And so this bottom one actually is a fraction. Is a constant. I just don't want to plug that in because I want to show you what I want to show you that if you have a variable in your summation that does not have to do with the index at all, that does not involve the index at all, then you could go ahead and factor that out because it's not bothering anybody. The sum doesn't need that n value. It needs I. It doesn't need n because our index is I, not n. So we can actually factor that out. But before we do that, at the top, I notice I have a 3 and a 3, so we can actually factor out that 3 as well. So we can rewrite this to get, so let me do it down here. So we say space. This is n times the sum as I equals 1 of 3 times I minus 1 all over n squared. Yeah? Okay. Now I said, hey, here, make it in red so that you can see, this is just a fat constant. We're actually a small constant because the fraction is really big. The denominator is really big, actually. But it's just a big constant, and then so we can factor that out because it doesn't involve I. It doesn't involve I at all. So we don't have to iterate through those. We can save ourselves the time and the trouble and factor that out. So that's actually what we're going to go ahead and do. So if we factor that out, right, we're going to get 3 over n squared from n I equals 1. And now since we factored that out, all we're left with is I minus 1, which is a lot easier to deal with because I have formulas for I and I have formulas for a constant. Because this is the same thing as 3 over n squared times the sum of n I equals 1 of I minus the sum of 1 from I equals 1 to n. Okay? And we already know how to evaluate these formulas. We just went through all those properties, so we can go ahead and plug it in. Remember that the formula for I was n plus 1 all over 2, and then minus nk, n times 1 in this case. And I can leave it as n because my end index is n, and I'm going to keep it like that for a reason towards the end, so that we can introduce it for infinity. Okay, so now that we have that, we can go ahead and simplify. So what I'm going to do here is I'm going to get a common denominator for my inside parentheses. And I'm going to get 3 over n squared times, I'm going to leave this as n plus 1 all over 2. And then to get a common denominator of 2 to n over 2. And now we simplify that. So then we can make this one big old fraction. We'll get 3 over n squared times, and now I'm going to factor in that I'm going to distribute that n in, and I'm going to get n squared plus n minus 2n all over 2. Which gives me 3 over n squared, and now I can combine n and negative 2n to get negative n all over 2. Now notice that actually I have 2 n's down here at the bottom, and then I have an n here and an n here, so I can basically factor it out and cancel them. So I'm going to be left with 1 here. This is going to be 1, and this is just going to be a big old 1. So that's going to go completely away. And so this problem's kind of long, but it's good. Lots of practice. So we get 3n over n minus 1 all over 2. Now we simplified it, and at the very end, we're going to get 3n minus 3 all over 2n. So this is what, maybe I should move that up a little bit. There you go. So to evaluate this function here, or the summation, when we simplified it, we got an equation for it, and we used the properties of our summation in order to get those properties. Now, what we want to do now is I want to plug in n equals 25 because I wanted to evaluate it for n equals 25. So let's go ahead and evaluate for n equals 25. Before we do that, let me move over to the next page. And let me copy this over so that we have it, so we can use it. Okay, so for n equals 25, all we're going to do is plug it in. We're going to get 3 times 25 minus 3 all over 2 times 25. So this is going to be what? 75 minus 3 over 50, which is the same thing as 72 over 50. They're both divisible by 2. 72 divided by 2, that's 36. And then over 25. So that's our answer. So now you're like, okay, why did you make me use n if we were just going to plug it in anyways? Well, here's what I want to do next. Is we evaluated this sum for, oh my goodness. We evaluated this sum for n equals 25. But what we're going to do later on in this section, maybe in part 2 or part 3 of 5.1, is I want to see how big I can get n so that I can get a really accurate answer for approximating an area under a curve. Right now it seems confusing, but I promise that when we get to it, you'll be like, ah, that's all we're doing it. So the reason I wanted to do it for n is because now we have a formula for our value, for our summation. So now we know that the sum, right, as I goes from 1 to n of 3i minus 3 over n squared is equal to 3n minus 3. Wow, that was a horrible 3. All over 2n. So we just found out that the formula for this, to evaluate this, is this, and now we can do it for any n. It doesn't matter what n is. If I tell you do it for n equals 3, n equals 10, n equals 11, n equals 1,000, n equals 10,000, you can do it, just plug it in. Now you have that formula, easy peasy, because right here I only gave you 1, but what if, and actually let me write this down. What if n equals 1,000? Or what about n equals 10,000? Now for n equals 1,000, we'll get that the sum is going to be equal to 3 times, yes, 1,000 minus 3 all over 2n. Oh, all over 2 times 1,000. And if we plug that into our calculator, we'll approximately get 1.49995. Oh, wait, no. That's for the next one. We'll approximately get 1.4985. And then for n equal 100,000, if we plug that in, we'll get 3 times 100,000 minus 3 times 2 times 100,000. And then here we'll get 1.499995. So notice these two answers are not too far off. Interesting. So what if we just did it for 1,000 and we just did it for 100,000? What if we just did it for n equals infinity? Now I can't really just plug in infinity, so what I'm going to need to do is I'm going to need to take the limit. So now let's go on to our infinite sums. Is we can do this problem for n going to infinity and just look at the long run behavior of this sum. And this is something you'll actually talk about a lot in your Calc 2 class, but you'll obviously go into more depth for it. But this is a really good introduction of, hey, for these sums, you can take the limit as n goes to infinity. And when you take the limit as n goes to infinity, you'll get n I equals 1, 3i minus 3 over n squared. So if I asked you, hey, evaluate the sum, how would you do it? Well, you already know what this is equal to, this part here. This part we already found out. This was 3n minus 3 all over 2n. We found that out up here when we evaluated for n. And so then we'll get the limit as n goes to infinity of 3n minus 3 all over 2n. And I think you know where I'm going from here. Now it's just a limit problem. Now it's just a limit problem. So then we'll get the limit as n goes to infinity of 3n over 2n minus 3 over 2n. These will cancel out. And then here, as n goes to infinity, this goes to 0. So my answer here is 3 over 2, which is equal to 1.5. 1.5. Well, when I did it for 1,000, I got 1.4985. When I did it for 100,000, I got 1.499995, which makes sense. So that tells us as n gets larger and larger and larger, that for our summation, it's going to converge to 1.5, which is a Calc 2 concept, but I just want you to take a look at it here. So now when you go to Calc 2, I already know what's happening a little bit when we get into these summations. Okay, now I was gonna do more examples, but I think it's kind of a long video. I just get excited with summations, I guess, right? So I'll put the 2 examples that I wanted you to write down and I'll tell you the answer for them, but go ahead and practice them. It'll be good to practice. Let's do this one. I want you to try this. I'm not going to tell you how to do it, but I want you to try the limit as n goes to infinity of n I equals 1 of 2i over n times 2n. Oh, times 2 over n. Okay, so I want you to try this one out on your own. Actually, let's do this one and then the last one you'll try on your own. Just so that You can see an infinity problem one more time from the start, because I realized that this one was tacked on to an example we already did. So let's do this one from the start. And then the last one you'll do on your own, promise. Okay, so here we have the limit as n approaches infinity of the sum as I equals 1 all the way to n of 2I over n times 2 over n. Okay, so what I'm going to do here is now I'm just going to multiply this out just to see what happens. So I'm going to get the limit as n approaches infinity. And so we want to write the limit again because it's important to keep that notation because we haven't evaluated anything yet. So I do have a comment on this on your exams. I did notice a couple of you guys, when you guys were doing the limits, you guys were not, it's fine if you don't write the limit if you're doing some side work. But at the end, you have to say the limit. So just remember to keep that consistent and that story going, because if you're not writing the limit, then you can't say, like, for example, I was going to simplify this to be 2I, sorry. I forgot the sum. To be 4I over n squared. Well, you can't say that this is equal to this if you take off the limit, right? That's not necessarily true. So you have to make sure that you keep that limit there. If not, then that's not true, and that's actually really wrong. So don't do that. Okay, so moving on. And so now what we want to do is we want to evaluate this limit. And so to evaluate this limit, what we're going to do is we're going to factor out that 4 over n squared, because remember, again, here, this 4 over n squared has nothing to do with I. Our index is I. That's what we need to keep in the sum. But as long as we don't have an I in this doesn't involve I, then we can factor it out. So let's go ahead and factor it out. So this equals a limit as n approaches infinity of 4 over n squared times the sum of I equals 1 of n times I. And now it becomes an easier problem because you already know how to solve this, right? You know the formula for this. So this is equal to the limit as n goes to infinity of 4 over n squared times n plus 1 all over 2. And we're multiplying them. And so now if we simplify this a little bit more, we'll get the limit as n approaches infinity. Notation is super important. Times 4 over n squared plus n all over 2n squared. And now we can evaluate this limit as we go to infinity. And here we'll get infinity over infinity, but you can apply L'Hopital's rule. And if you apply L'Hopital's rule, here I will give you the answer. You'll end up with 2. Or you can kind of see what's going on because the numerator and the denominator have the same constant. So you know that they're both gonna, when we take the derivatives, they're gonna come together at the same time. They're gonna both simplify to 1 at the same time. So if we just take the leading coefficients, those simplify to be 2. So now I want you to try the limit as n goes to infinity from I equals 1 to 4i squared I minus 1 of n to the 4th. And I'm going to go ahead and give you the answer. This actually converges to be 1, but go ahead and try it on your own. It's good for you.
Do your homework.